Hey guys, welcome back to the channel. As you may have heard on the news, the weather has been a little bit crazy for the past few months out here in California, so I have not been able to image at all. That being said, I do have an exciting topic for you today. This video is going to be an introduction to amateur spectroscopy, which is a wonderful and exciting field to get into, especially once you've mastered the basics of astrophotography. I'm also going to tell you a little bit about this, which is a high-resolution spectrograph I recently built using my 3D printer, and what this little guy can do is going to literally blow your mind. So welcome to the wonderful world of spectroscopy, and let's get started. I've always loved creating beautiful images of the night sky. To me, astrophotography is the perfect blend of art and technology. But I've always wanted more out of this hobby than just a pure aesthetic pursuit. I first and foremost enjoy learning about the physical nature of the beautiful objects in the night sky. And the best tool available to astronomers to probe the physical properties of a distant astronomical object is a spectrograph, which allows us to measure the properties of light over a specific portion of the electromagnetic spectrum. I'm sure you've seen some of the beautiful images recently captured by the James Webb Space Telescope. One thing that you may not realize about JWST is that it actually spends most of its time acquiring spectra instead of pretty images, because a spectrum reveals so much more about the true nature of an object than a photograph will ever be able to do. So until about a year ago, I was under the impression that amateur astronomers interested in spectroscopy were limited to something like the star analyzer, which is an affordable diffraction grating that is very convenient because it is mounted like a filter. And so it's very easy to pop it into your filter wheel and start acquiring spectra with the camera. Unfortunately, the star analyzer has a limitation in that it does not have a slit, which makes it impossible to ensure that you are getting only light from the target that you are studying. And it also makes it impossible to properly calibrate the spectrum that you obtain. So while Star Analyzer is a great and very affordable way to give spectroscopy a try, it's not really a scientific tool. About a year ago, I looked at other options, and I stumbled upon a French company named Cheliac Instruments, which sells high-quality spectrographs like the LP600 or the Libres 3. Unfortunately, these high-quality instruments were slightly out of my budget. But then I read about a project named SOLEX, or Solar Explorer, created by Christian Buil, a famous amateur astronomer in France who was a pioneer in the adoption of CCD cameras back in the 70s, 80s, and 90s. And Christian has been doing spectroscopy both as an amateur but also as a professional for over 40 years. And he even worked on spectrographs that have been launched into space. SOLEX is a spectroheliograph. Basically, it is a spectrograph that you can use to create amazingly detailed images of the sun at pretty much any wavelength, like H-alpha or calcium K or H, for example, depending on what you are studying. Here is a high-resolution image of the sun in H-alpha, captured using SOLEX, attached to a small 80mm refractor by Olivier Aguerre. And here are a few images by Guillaume Bertrand using a small 72mm refractor in H-alpha, calcium H, and finally a map of the sun's magnetic field. This last one is what is known as a magnetogram. Creating such an image is a little complicated and far exceeds the scope of this video, but if you're curious, it uses the Zeeman effect, which is the splitting of spectral lines in the presence of a strong magnetic field. When Christian designed SOLEX, he wanted to strike the right balance between affordability, performance, ease of use, and extensibility. So he made it possible for people to build the project on their own using a 3D printer and a reasonably affordable optical kit that you can purchase from a variety of vendors, including Cheliac Instruments. Building this spectrograph teaches you a lot about how the instrument works, how to properly tune it, how to maintain it, and I think there is a lot of satisfaction in using an instrument that you have built with your own hands. It's really a lot of fun. Also, if you have a mishap down the road, you'll know exactly how to repair the instrument. Christian also designed an extension to SOLEX named StarX, or Star Explorer, which turns SOLEX into a traditional spectrograph designed to capture the spectrum of dim objects in the night sky with a telescope. And this is what we are going to talk about today. StarX is an affordable way to get into the wonderful world of spectroscopy. The optical kit costs about $500 and it is a very powerful scientific tool, as you will see in this video. Up until now, the SOLEX and StarX projects have been known mostly in France, since that is where the project started. My goal over the next few months is to help introduce spectroscopy, and more specifically the StarX project, to a worldwide audience. My goal is not to repeat all of the information that Christian has painstakingly put together on his website or in his YouTube channel, which I strongly recommend you check out. I'll put a link to his YouTube channel right here. Instead, I want to present my own perspective on the project. I consider myself a beginner in spectroscopy, and therefore my experience may be interesting to some of you. So this is going to be a multi-part video series. In this first video, my goal is just to entice you. And to do that, I am going to start by showing you a few sexy results that I have already obtained, and I will also show you results obtained by other amateur astronomers, some of which are going to quite literally make your head explode. In future videos, I'll show you how I use StarX with my telescope, and how I acquire spectra using only free software like Nina and PHG2 guiding. I'll also talk about an important topic, which is spectral calibration and the processing of 2D spectra into a spectral profile using a piece of software called SpecNT. I will produce a few more videos throughout the year to cover a few fun topics. For example, I'll show you how you could use StarX to test your own astrophotography filters, similar to what Creve the Lazy Geek has done in some of his recent YouTube videos, but with a resolution 40 times higher than what he was able to achieve. And so this setup is ideal to test narrowband filters. We'll also use StarX to analyze my local light pollution, or to scientifically estimate the amount of chromatic aberration in a refractor, and many other fun things. I don't have an exact list of topics, but I'm sure that I'll have plenty to talk about. So if you are not yet a subscriber, now is the time to click that subscribe button. Also click like, it helps the channel. Alright, let's look at what a small spectrograph made of plastic that you can build entirely by yourself for about $500 is capable of in the hands of a beginner. Before I show you some of the results I have obtained, let me explain something important. I currently use my spectrograph in high resolution mode only. This is primarily a function of the grading that I use, which has 2400 lines per millimeter. With that, I get a resolution of 18,000, which means roughly 0.4 angstrom or 0.04 nanometer around the H-alpha wavelength, which when you think about it is kind of crazy because in astrophotography we call 3 nanometer bandpass filters narrowband, and this little spectrograph here has a resolution that is 1/100th of the bandpass of a narrowband filter. In that mode, my spectral coverage is roughly 200 angstrom, so it's a pretty narrow window into the electromagnetic spectrum. But the resolution allows you to see rapid changes on stellar targets that sometimes happen in a matter of hours, and I find that completely fascinating, so that's what I've been focusing on. Also, calibration is a lot easier in high resolution than it is in low resolution. That being said, it is possible to use StarX in low resolution mode, which allows you to see a larger part of the electromagnetic spectrum all at once and to target even fainter objects, and we'll do that in future videos. All right, let's look at some of my early results. This first set of images was taken using an OSC camera attached to the spectrograph and pointed at a white wall illuminated by the sun. There was no optic in front of the spectrograph. I slowly rotated the grating and took a picture every time I saw something interesting. So what we are seeing here is the spectrum of the sun, and in this first image we see the famous H-alpha line in the deep red part of the spectrum at 656 nanometers. It is the first line of the Balmer series. It is dark, meaning that it is an absorption line, because the sun's atmosphere, which is made primarily of hydrogen, absorbs light exactly at that wavelength. Next, in the deep blue part of the spectrum, actually in the near UV part of the spectrum, since we're at 3900 angstrom, we can see the Fraunhofer H and K lines, which are caused by singly ionized calcium, or Ca2. Next, in the green part of the spectrum, we can see a trio of lines, which are caused by magnesium. By now, you're probably wondering how I know this. Well, you can use a spectral reference like this one, which was created by Olivier Garde using an échelle spectrograph, which is a very special kind of spectrograph that gives you both a very high resolution and a very wide spectral coverage. Okay, let's continue. Next, in the yellow part of the spectrum, we're seeing the famous D lines caused by sodium. By the way, you can try at home to throw some salt onto a natural gas burner and you'll see a yellow light appear. If you were to look at the spectrum of that yellow light, you would see the same two lines caused by the sodium that's in the salt, but in emission this time. The fact that we have two lines very close to one another, separated by about 6 angstrom, is caused by a quantum mechanical property of the electron called the spin. I'll keep it at that, but in a future video I'll tell you about excellent books on the topic that explain how spectral lines are made. And finally, in the near infrared, starting at around 7600 angstrom, we're seeing a band of absorption lines. These are not from the sun, they are caused by the molecular oxygen in the Earth's atmosphere. Next, we are looking at our first nighttime target. This is the spectrum of Beta Lyrae, also known as Cheliac. This image is exactly what comes out of my camera when it is connected to the spectrograph. Cheliac is a famous Be star. So it's a B star, which means that it is young and hot, and Be because its H-alpha line is in emission, which is unusual for a star. And you see that emission right here. There is another emission line further to the right, and that one is caused by helium. These emission lines are caused by a shell or a disk of gas orbiting around the star. These objects are the subject of much research, and amateurs, including myself, are constantly contributing new spectra of Be stars to a ProM database, and these spectra are used by professionals to refine their stellar models and to glance additional insight into these curious objects. If we stretch this image, for example in PixInsight, we will see a few vertical lines, which are calibration lines. In this case, these are injected into the spectrograph using a small neon bulb. I will talk more about calibration in a future video because it's a slightly complex topic. What you should know right now is that these calibration lines are used by the software to figure out which pixel corresponds to which wavelength, and that is how we are able to go from this image, which is called a 2D spectrum, to a calibrated spectral profile like this one. Our next target is a planetary nebula in the constellation Cygnus, known as NGC 6826 and often referred to as the blinking planetary, because if you observe it visually, it is easily visible when using averted vision, but almost completely disappears when you directly look at it because the brightness of the central star overwhelms the eye. So what you are seeing here is pretty interesting. You are not seeing the image of the target. Instead, you are seeing the slit itself. But the slit is rectangular, so why would we see an oval instead? That is caused by something called the Doppler effect. Basically, the gas that makes up the nebula expands at a fairly high speed from the central star, and that radial velocity causes a shift in wavelength. The part of the nebula that is moving towards us sees its light shifted towards the blue part of the spectrum, while the part of the nebula that is moving away from us sees its light shifted towards the red part of the spectrum, and that is why we are seeing an oval. By measuring the width of that oval, we can precisely measure the speed of expansion of the nebula. In this case, I measured a radial expansion of 50 kilometers per second, which is confirmed by the scientific literature on this object. The brightest oval in the center is the H-alpha line. We are seeing very weak ovals on either side, caused by singly ionized nitrogen, or N2. These are so-called forbidden lines because they cannot be reproduced in a laboratory on Earth due to the extremely low pressure required. This goes to show that our universe is a giant laboratory and astronomy can teach us things about nature that we would not otherwise be able to understand. If we now look at the famous Messier 57, also known as the Ring Nebula, in the summer constellation Lyra, we can see these forbidden nitrogen lines a lot better. We can even see faint lines to the right emitted by helium. Another target that I studied last fall is WR134, which is a Wolf-Rayet star located in the constellation Cygnus. There was a recent article about Wolf-Rayet stars in the February 2023 issue of Sky and Telescope magazine. I recommend you check it out. This wonderful image was captured by my friend Francisco Meschia, and it shows the nebula created by WR134. If we look at the spectral profile of that star around the H-alpha wavelength, we see a very wide emission line. If we assume that this is only the H-alpha emission line broadened by the Doppler effect, we can measure that the star indeed has very strong stellar winds, and the radial velocity of that stellar wind is about 2,000 kilometers per second. In reality, it's not that simple. WR134 is classified as a WN Wolf-Rayet star, which means that it has a weak H-alpha line. What we are seeing here is likely a blend of H-alpha and helium-2, and so the radial velocity measurement may not be fully accurate. But still, this was a fun result. Also, you may wonder what those humps and bumps are in the spectral profile. Well, some of those are what we call telluric lines, basically absorption lines caused by the Earth's atmosphere. Others are co-rotating interaction regions, or CIR, which were recently discovered during a PRO-AM research project a few years ago. They change over time, whereas telluric lines stay in the same position, and that's how we're able to tell them apart. Okay, last one. What would you say if I told you that I imaged a black hole right here from my extremely light-polluted backyard in San Jose, California? Would you believe me? Well, here is a 2D spectrum of an object known as SS433 that I acquired last summer. This is a high-resolution spectrum taken with a small telescope, so the signal-to-noise ratio is not so great, but it shows the H-alpha line in emission, which is caused by the accretion disk around the black hole. Yes, SS433 is what we call a microquasar. It is located in our galaxy, and it is made up of a black hole and a large star of spectral type A orbiting each other. The companion star rapidly loses mass into an accretion disk that forms around the black hole. That's why we're seeing the H-alpha line in emission. Additionally, there are relativistic jets emitted by the black hole perpendicular to the accretion disk, and we can see those jets in a low-resolution spectrum like these. In France, last summer, a number of amateur astronomers banded together and captured low-resolution spectra of SS433 over a 3-month period. Christian Briel put them together, and here's what he got. We can see the jets preceding, kind of like a spinning top, right before it stops spinning. Additionally, we can see oscillations with a much lower period. These two phenomena are due to the influence of the companion star. If you would like to learn more about SS433, I can recommend this book titled The Quest for SS433 by David Clark, which recounts the discovery of this highly unusual object. You can find this book used, and it's a little bit dated now since the events took place about 40 years ago, but it's still a fascinating story. If you would like to learn more about what a spectrograph like StarX is capable of in the hands of someone with more experience than I do, I encourage you to check out Christian Buhl's website at this URL. Some of the results that he's been able to obtain are simply amazing, and maybe I'll cover some of these on the channel, if I'm able to reproduce some of the observations myself. In case you have not already noticed, I am pretty excited about amateur spectroscopy. Right now it's still a bit of a niche, but if we had more people able to contribute quality spectra, we could undertake ambitious research programs in partnership with professional astronomers, and that I think would be really cool. Okay, that's all I have for you today. If you enjoyed this video, please give it a like. Also, don't forget to subscribe to the channel so that you don't miss future videos. We will come back in a few weeks with another video, so until next time, thank you for watching.